let us say my battery voltage rated equal to 4.2 volt, right, and somebody tells you, okay, I have a reference of 1 volt. You are familiar with non-inverting amplifiers. So, if you now put a non-inverting amplifier that is capable of providing current and connect that to the battery, it will automatically come to the rated voltage of the battery, as long as you choose the feedback elements properly. So, let us try to do that. So, let us say I have a non-inverting amplifier. This is Vref, which is 1 volt, and then this is the node I am going to connect to the battery, which is my output voltage. So, here V desired is 4.2 volt. So, what can I do? Let us say I have R1 and R2. I can say that let me choose this to be 100K, then I will choose this to be 320K. So, now the overall gain is, that V out, which is V out. So, we will call this V out. V out by Vref is 1 plus R2 by R1, which is 1 plus 3.2, which is equal to 4.2. So, V out is equal to 4.2 into Vref, which is 4.2 volt. So, it matches with the V design. So, now this is a you can, as a first step, say, yeah, this is my proposed battery charger. Whenever somebody plugs it in, plugs the wall power in, I am going to activate this op amp. So, this op amp will now in this closed loop configuration is now going to drive that V out towards 4.2 volt, right. So, that is going to happen, correct. There is nothing wrong in all of those statements. The one gap in that statement is, okay, it is going to get to 4.2 volts, but what is the current that is going into the battery, right? Is that current regulated? Is that current controlled? Can you tell me what that current is? That is where this approach needs some tuning. So, what we are going to do is maybe just take a step back. Let us try to go back to something we learned long ago in RC circuit. So, let us say this is now Vbat. Let us say this capacitor, I am going to call this voltage as V out, and I am going to say that initially at time equal to 0, this capacitor was charged to a voltage of V in. So, let us say this is R, this is C, right. Now, at some level the equivalent circuit for that non-inverting feedback amplifier would be something like this. We will get there in a minute, but that is the reason we are starting with this. What we are going to now try and do is say, okay, if I had an equivalent circuit like this, how will V out look versus time, and let us say I put a, so let us say I am going to put one ammeter. You always connect an ammeter in series, and I am going to maybe here put a voltmeter, and voltmeters are always connected in parallel. So, how will this voltmeter and ammeter look as a readings look as a function of time? That is what we will try to answer. So, I am not going to work through every step, but I think you know that V naught is equal to V in plus V bat minus V in into 1 minus e to the minus t by RC, right. I just so let us quickly do and check to make sure I wrote it correctly. So, now at t equal to 0, what happens? E to the minus t by RC goes to 1. So, this term completely vanishes. So, I get V naught equal to V in. At t equal to infinity, what happens? At t equal to infinity, e to the minus t by RC goes to 0. So, this is V in plus V bat minus V in. So, V out is equal to V bat. So, sounds about right that V out will be V in plus V bat minus V in into 1 minus e to the minus t by RC. So, you can say that this is what the voltmeter will show. So, a function of t, let us say this is V in, let us say this is V bat, the voltage, the voltmeter will show something like this, right, where this is an e to the 1 minus e to the minus t by RC type of curve. This is what the voltmeter will show. Now, let us look at what the ammeter will show. So, there are two ways to do this. One thing is to say that what is the ammeter, I mean these two are, there are only two elements in the circuit, there is the resistor and the capacitor, which means they are in series. So, current flowing through the resistor has to be equal to current flowing through the capacitor, and it is good to validate that okay, whatever way I calculate I get the same answer. So, current, switch current. So, I am going to first calculate current flowing through the resistor R. What is the current flowing through the resistor R? It is V bat minus V naught by R, right. Let us do one thing, let us just so let us switch to a new page. So, we will just start by, so again this is our so, what I have done is I have just rewritten that stuff here. Now, like I said, R and C are the only two elements in the network here, and which means current flowing into one component, all of that current has to flow into the other component. So, first let us calculate the current through the resistor. Current through the resistor is just the difference in voltage between its two terminals divided by the resistance. So, this will be V bat minus V in minus V bat minus V in into 1 minus e to the minus t by RC by R. So, I can pull out V bat minus V in by R, then I get 1 minus e to the minus t by RC, right. So, it is V bat minus V in by R into e to the minus t by RC. So, the current flowing through the resistor is V bat minus V in by R, whatever is that initial current, and that initial current then is going to decay with a time constant of RC. Now, it is worth validating that whatever current we calculated as flowing through the resistor is also flowing through the capacitor. So, we will calculate the current through the capacitor. How do we do that? The current through the capacitor is essentially driven by the rate of change of charge. So, it is C dE V naught by dt. So, we have the capacitor C, and now we are going to differentiate V naught. V in is a constant, so when you differentiate it, it will disappear. So, we have V bat minus V in into again d by dt of 1 minus e to the minus RC, 1 is a constant, so it is going to go away. It will be into minus 1 into d by dt of e to the minus t by RC. So, it is e to the minus t by RC into minus 1 by RC is the differentiation of V naught, right. So, IC will be equal to 1 by R into V bat minus V in into e to the minus t by RC. The capacitor gets cancelled out in the previous term. So, you have V bat minus V in by R into e to the minus t by RC. So, these two match. It is just again you fully expect them to match. It is just good to do this to be sure that okay, I did not do any silly mistakes anywhere, right. Whether you are doing design, whether you are doing finance, whether you are whatever activity you are doing, it is always good to have a system of checks and balances that you know okay, I am going to at all times look at a left hand side and a right hand side and make sure that they tally off, so that I know that I did not make any silly mistakes. So, we have now gotten the correct expression for the current. So, let us now go and try to plot this current. So, how will our ammeters look as a function of time? So, what the ammeter will read as a function of time is at t equal to 0, it is just going to read V bat minus V in by R, and then that okay. So, it is going to read at t equal to 0, it is going to read V bat minus V in by R, and then this current is going to exponentially decay. This exponential decay will be of the form e power minus t by RC, with the time constant is RC, right. So, now let us go back to the charger for a second, right. I mean, why did we do all this? So, one of the things we wanted with the charger was to say that if you are going to charge the battery, it is important that the battery is not being charged at a faster rate than it can handle, which again becomes a safety hazard. So, it is important to regulate the current. Now, the problem with a circuit like this is that there is no regulation on the current. The current will start with some very large number and then it will decay, right. So, let us now sort of try to go from this exponential characteristic, right, and try to think about, okay, we know we talked about RC circuits, but we were really talking about a battery. Suppose this is a parallel for the battery, what would that capacitor look like, what will that resistor look like, how do I wrap my head around the type of numbers I am dealing with. Let us try to sort of untangle that a little bit. So, first thing we should maybe recognize is, and this might have been taught to you in one of the earlier modules, and I think it was covered in the video as well, where you can think of a voltage source as an infinite capacitor, right. A voltage source is indistinguishable in its characteristic from an infinite capacitor. You can think of a battery as a slightly voltage source, but not ideal. So, maybe it is a very large capacitor, right. So, let us get to that. So, is the battery a capacitor? If so, how large is its capacitance, right. Again, you know, now Puritans might disagree with some of these statements I make about capacitor capacitance. I think part of engineering is to say that yeah, I know what I am saying is not 100% accurate. As long as I know where I am making assumptions and I am blessing off those assumptions with good reasons, it is okay to do so, right. That is the model with which we will continue to operate here. So, know that some of these things on okay, what is the equivalent circuit for a battery only a capacitor, or is it more complex than that, not for us to get into here. For the purposes of this conversation, perfectly okay to assume that the battery is a large capacitor, right. So, now let us try to calculate what that capacitance might be. You know, when you buy a cell phone, for example, one of the things they tell you is, oh, I had this comes with a 4000 mAh battery, right. Or when you buy an electric vehicle, they will again tell you, okay, you know, it's maybe so many ampere hours, 3 ampere hours, 4 ampere hours of battery. So, the milliamp hour or ampere hour is a unit that is used quite frequently for the battery. And you think about what unit is that, right? It is essentially current multiplied by time, and current multiplied by time is charge. So, what they are saying when they say 1000 mAh, 5000 mAh or 5 ampere hour is essentially telling you this is the amount of charge that that battery can hold, or that capacitor can hold when it is fully charged. So, let us say I have a battery that is my battery is a lithium polymer battery, lithium polymer battery. So, I have 1000 mAh with VBAT rated of 4.2 volt. Let us say this is our battery, we are building a portable device. This seems like the same kind of battery that you can use for a portable device. Phones use 4-5 times this size now, maybe even more. So, now let us say my Q is equal to 1000 mAh, right. The first thing I want to do is convert this into a unit that I am used to with charge, which is coulomb. So, how do I go from a milliamp hour to coulombs? I am going to say this is equal to 1 ampere hour, which is 1 ampere into 1 hour. So, 1 ampere into 3600 seconds, which is 3600 ampere seconds, right, and an ampere second is a coulomb. So, this is 3600 coulomb. That is the amount of charge that is being held in that battery or in that capacitor, right. And now you might want to say, I want to estimate the capacitance itself. We will say, Q is equal to C times V. My battery is rated to 4.2. So, now C is equal to Q divided by VBAT rated. So, this is going to be 3600 coulombs by 4.2 volt, which is about 860 or so farads, right. Very large capacitor. So, you can think of the battery as a 860 farad capacitor, and you can say, now let me go back to the time constant. That time constant was what? It was RC, right. So, if I had 1 ohm, that means that my time constant is now 860 seconds, almost 15 minutes. That is the time constant for that battery. Now, that resistance is not going to be 1 ohms. So, let us talk about that resistance also for a bit. So, let us say again, suppose I go back to that amplifier and say I have Vref, my 100 kilo ohm, 320 kilo ohm, right. Let us say this is coming from V bus. V bus is 5.5, whatever you are getting from your adapter, right. So, now that we have this feedback amplifier, one of the questions that we have to answer is, we were talking about an RC time constant, and when we have that RC time constant, what is this resistance? What is R out, right. Now, you can argue that R out is going to be very small because I have a feedback amplifier. I have put a large gain in that op amp, and that gain multiplied by the attenuation factor is my loop gain, and RO divided by 1 plus loop gain is my output resistance, and that will be very low because my loop gain is high. I am building a voltage control voltage source. Voltage control voltage sources will have low output impedance because they have to supply a lot of current, and so everything that about these set of statements, that loop gain is large, so output impedance is low, it is a voltage control voltage source, so by design output impedance will be low, all of those statements are correct. So, what contributes to the R out? What actually contributes to the R out are physical things like wires. So, you might have seen this, right, with batteries that you have. When you connect the battery, when you look at the battery, there will be typically 2 leads from the battery that will go connect to the PCB. Those leads have resistance. The battery also has resistance. Any routing that you do after your feedback circuit to the battery will also have resistance. So, you can sort of think of it this way. You can say that okay, there is some R wire here that is going to contribute resistance, and now when I come to the battery, maybe my battery is not a perfect capacitor, right? Maybe it has some internal resistance of its own that also has to be factored in. So, these are the ones that will contribute. So, let me just move this here. So, these are the resistors that will contribute to the time constant now. So, now you can again, one way is to say that okay, I am going to open the PCB, I am going to look at the trace length and width, I am going to look at sectional area, calculate rho by A and then rho by A into L, that is how I am going to estimate the resistance. Or you can say okay, let me see, I have a 1000 mAh battery. I will usually when they when they talk about the battery's capacity, the rated capacity of the battery is also called 1C. So, if I have a 1000 mAh battery, that 1000 mAh is called as 1C, and typically they advise you to charge the battery at rates no greater than 1C. In some cases exceptions are made, but the typical advice, general advice for, unless you spent extra with the type of battery, have special protection circuits etc., is to say that you limit yourself to 1C type of charging. That will give you good aging characteristics for the battery. So, with that you assume okay, I have a 1000 mAh battery, maybe I am going to charge it with 1 ampere of fast charge current, and I am willing to tolerate maybe a 50 millivolt drop. So, R wire and R bat put together has to be in that 50-100 millivolt. Right? That is how you would think about it. It is possible it might be little higher, but at least for the purposes of first calculation you can say oh, okay, now if I have to go back to this RC circuit, right, that we originally were looking at for calculating current and voltage characteristics, you can say that okay, now in the context of a battery, maybe if I look at R and C again, I would say that okay, for a battery R is maybe 0.1 to 0.2 ohms and C is, we calculated C, it is about 860 farad. So, 0.2 ohms into 860 farad is what, about 173 minutes or so, 180 seconds, roughly 3 minutes of time constant. Now, the initial current, right, if you remember, IR initial is just V bat minus V in by R, correct. Let us say I had discharged my battery to 10%, then I am going to plug in. So, my battery maybe V in is maybe at 3 volt. So, in that case, if V bat is 4.2 and V in is 3 volt, R is 0.2 ohms, the initial current flowing into the battery is 4.2 minus 3 by 0.2, which is 1.2 by 0.2, which is 6 amperes, right, very large. Obviously, I do not want this level of current to be flowing into my battery. So, what which comes back to the challenge with this circuit. So, if I go with a op amp based non-inverting amplifier with no regulation in current, then the peak current that happens that is charging the battery might become very high. So, I have to now come up with a way to say that okay, let me minimize that current, let me see what I can do to keep that charging current or control that charging current, regulate that charging current, and I also have to be able to choose a preconditioning current, or that is a fraction of this fast charge current. How can I do that? That is what we are going to look at next.